All right. Our initial coast solution also had somewhat of magic cows in that they sort of instantaneously went from uh, a small cow to a big cow without feedbacks on the fodder. We're going to change that a little bit here. And so I've set up the same problem. We have the same 10 acres, same productivities, same uh, same total weight, same 50 cows, same 500 starting pounds, and the same growth rates. The difference is here we're going to create a dynamic equation where as they get bigger, of course, the fodder doesn't make them grow as fast, and how would that affect our solutions? But largely we're just doing this to show how we might solve a fairly complicated dynamic model using Solver, because that's the tool of the day. And so we start off with the weight on Bill's is just the D5, and the weight on Madison's is the initial weight that they put out there. Then in the next period, the weight on Bill's is the previous weight plus the growth. Okay, so it's the D2, which is the fodder minus the total weight times the 4 pounds again. So if they're eating more than they need, they'll grow. If they're eating less than they need, then they'll get smaller. Our scaling factor, and then again the previous weight. And this has just been copied all the way down. And because they don't gain any weight on Bill's land at 50, they stay at 2,500. So in Madison's land, in the first stage, they gain the weight, and they move down. And so it's this. Here it's just the one, and this one is the same equation as before, except we're using the weight on Madison's land. And you see we're using the same equation. They do actually grow a bit, and we're great. So the total gain on Bill's land is the 25,000 minus what has been the initial weight. And the total gain on Madison's land is the total weight we started with on her land, or what we've gained minus that. And I just put the total gain of Bill over here times 0.9, which is the cost per pound, the price per pound in wholesale markets. And the same thing here. So they both get 90 cents. So we put this in terms of dollars just to do it. All right, so I'm going to take and select both of these, all of these, and slide down to our 30th month. And then, so we have here, these are just copies of these two. The total at the bottom, remember these are totals because they're subtracted from the previous. It's dynamic. These are not what we make. And this is our total weight and our total gain. And so we have these both here. Bill hasn't gained anything because his cows still weigh the same. They're just on a maintenance diet. And the ones on Madison's land have gained a lot. So our total money is both the money made off Bill, which is nothing, and the money made off Madison, which is 22,000 something. And so that's what we're going to want to maximize in this case. So we'll go back to our data and solver, and what we want to maximize is the total money, which is H39. And we want to change the cells way back up here, the number of cows on Bill and the number of cows on Madison's. Right, and again, the constraint is they can't have more than 100 cows. But this is a feedback situation where your cows get fatter and compete with each other and don't magically grow to the end. And so we have this dynamic solution that we need to solve. The calculus of variations on this would be unpleasant, so we use Solver, and we're going to click Solve. And lo and behold, it tells us that when they compete with each other, Bill should actually have 10 cows on his land and 6 on Madison's would be our optimal solution, because we couldn't have partial cows. We could have set Solver up so these were integer solutions, and we'll play with that a little later when we solve the party planning problem. But so we go down to the bottom, and we end up a lot better off by restricting the amount of cows when they compete with each other. All in all, this was how to use our solver solution, and we will go into some of the more nifty things of solver later on in class. But wanted you all to see that we could solve the Coase solution. And again, the same Coase solution is there's an advantage to society, even though it was different than in the static, substantially different, for Bill to cheat and put his cows on Madison's land. And quite substantially more, and that society might be much better off, as you can see by the total dollars here from the 50-50 solution. The total dollars at the end of this time is far greater. So the idea that maybe we're better off when we restrict fishing or restrict access to resources where there's dynamic growth, we'll see over and over.